Find intervals of increase and decrease and local extrema for the function f of x. Okay, so as you've probably seen in previous examples, all these things are about the derivative. Increasing means positive derivative, decreasing means negative derivative, and local extrema means either the top of a hill or the bottom of a valley. Either way, it's a spot where the derivative is zero because the function is temporarily flat. So let's get a derivative. If you have not done trig derivatives yet, you're going to be slightly stuck by this one until I give you the following fact, which is the derivative of sine x is cosine x dx. Or the other way you might see it written places is d dx sine x equals cosine x. Or the other way would be sine x prime equals cosine x. It's all good. So if we go to do the derivative of this thing, don't start writing a cosine yet. The first thing you must do here is this power. This function is technically f of x equals sine x squared. And so when you go to do its derivative, the first thing that happens is you go 2 times sine x to the power of 1, and then the chain rule says you do the derivative of sine x, and you get cosine x. So 2 steps. Power rule followed by chain rule. And that is our df dx. We want to know where it's positive, and we want to know where it's negative, and we want to know where it's zero. And as you've seen in previous examples, probably, finding the zeros is the best way to proceed. If you know where the zeros are, then we can do our number line and see what's happening around those zero values. So, if 2 sine x cosine x equals 0, what solutions does that have? Either 2 equals 0, which is nonsense, or sine x equals 0. Where does that happen? Sine is your y coordinates, so sine x is 0 when the angle is 0, or 180 degrees, or 360 degrees, or actually I don't have to go any further because they told us to stop at 2 pi. And oh, notice this. They don't even want us to include 0, so this actually is not a value of interest for us either. Chop that out. So only pi and 2 pi are zeros from that piece. The other thing that could happen is maybe cosine x equals 0. When does that happen? If cosine is our horizontal coordinates, it goes to 0 at 90 degrees, when our angle is 90 degrees, or when our angle is 270 degrees. So there are the 4 zeros of our derivative. Let's get a number line and see how our function behaves around those things. So we have pi by 2. I'm putting these in increasing order now. So pi by 2, then pi, then 3 pi by 2, and then 2 pi. And we're going to search. We're going to look on and around those values and see how our derivative behaves. And our pieces are 2 sine x. The 2 isn't all that important because it's a positive number, but we'll keep it in. If you want to drop the 2, that's fine. You're going to get the same results that I will. Because multiplying by a positive number doesn't change anything's sign. Won't make anything go from negative to positive or vice versa, so the 2 isn't really contributing to this. Okay, so sine x. If we have an angle that's lower than pi by 2, like lower than 90 degrees, then we're in quadrant 1 and sine is positive. At 90 degrees, sine is still positive. Between 90 and 180, sine is positive. At 180 degrees, sine is 0. Between 180 and 270, sine is negative. At 270, it's still negative. This is like quadrant 4. It's between 270 and 360, negative. And at 2 pi, which is like 360 degrees, sine is 0. For cosine, if we're just below 90 degrees, we're in quadrant 1, so cosine's positive. At 90, cosine is 0. This is quadrant 2, cosine's negative there. 180, cosine's negative. Between 180 and 270, cosine's negative. At 270, cosine is 0. Quadrant 4, cosine's positive. And at 2 pi, which is like 0 or 360 degrees, cosine is positive. That means our derivative is plus times plus, plus times 0, plus times minus, 0 times minus, minus times minus. You get the idea. La la la, la la la. Okay. So, these are the signs of our derivative, which means they're the sign of our slope, which means this function's going uphill, flat, downhill, flat, uphill, flat, downhill, flat. If you think about it, it's not surprising that a sinusoid or a function made of sinusoids would do that. Sorry, that was an attempt at a drawing and it didn't go well. Uphill, flat, downhill, flat, uphill, flat, downhill, flat. Lots of trigonometric functions have that behavior where they just alternate back and forth and make a wave shape. So you can see your intervals of increase and decrease. I'm not going to write them out, but all of these intervals that are pluses are intervals of increase. The ones with negatives in them are intervals of decrease, and we might have a local extremum any place that the derivative is 0. Let's take a closer look at those. Here our function is going increasing, flat, decreasing. That's the top of a hill, or what we call a local maximum. So we have a local max at pi by 2. I'm going to say max at pi by 2, comma, and what's the height of our actual function there? We can go back to f of x and see how high it is at pi by 2, or at 90 degrees if you're happier thinking in degree mode. Sine 90 is 1. Square it, it's still 1. So we get a max at pi by 2, comma 1. The next interesting thing that happens is the function's going downhill here. It flattens out at pi and then starts to rise again. This point, right at pi, must be a local minimum. It's the bottom of a valley. We went down, flat, up. So we can say there's a local minimum when x is pi. And how high is the function there? Pi is 180 degrees. The sine of 180 is 0. Square that and it's still 0. So pi comma 0 is a minimum value. What next? Here we have increasing, flat, decreasing. So 3 pi by 2, it seems, is the top of a hill for this function. It's a local max at 3 pi by 2. And what's the y value? If this is 270 degrees, the sine of that is negative 1. Square it, you get positive 1. So there's a max. And finally, here we have decreasing. We get to 2 pi and the function flattens out there. Sadly, we don't look at, and we're not supposed to look at, what happens beyond 2 pi. So at this point, I don't know if the function continues to drop off, or if it rises, or if it continues flat forever. Probably not, but in theory it's possible. It's hard to know what's going on with a function when you only have the derivative on one side of it, but the fact that it's decreasing and then flat tells us that this might be a minimum, but we can't call it a local minimum because we don't know for sure that it's the bottom of a valley. We don't know the derivative on the other side. So this point, in my humble opinion, is disqualified from being a local minimum. To be a local minimum, you have to have a negative derivative on one side of you and a positive derivative on the other side. Doing this, even though it totally looks like you might be the bottom of a bowl, is not good enough. And so I would not count this as a local min. That's basically their fault for restricting the domain the way they did. They stopped this just barely too soon for us to make a decision about what's happening with the derivative on the right. So our list of local extrema would contain 2 local maxes and only 1 local min.